Right, we've looked at linear and circular motion, so now we need to look at oscillating motion, which is any rhythmic and repetitive motion around an equilibrium point. This motion is found throughout physics, so we need to have a really strong understanding of what's going on. Examples are a ruler on a table's edge, a wave, a pendulum, or a mass on a spring. Last two are the most important for our course, so that's what we're going to concentrate on, and I've got a pendulum here. So pendulum is just a mass suspended on a string. At the moment it's at equilibrium, which means that it's at rest, and if I displace it from its equilibrium position and then let it go, it'll start to oscillate. A rhythmic, repetitive backwards and forwards motion. Right, so we need to have a look at our terminology for our oscillating motion. I've drawn a pendulum here. The black one in the middle symbolises when it's at rest. Now, if I pull the pendulum away from its equilibrium position, I displace it. The displacement is the distance from the equilibrium position, the distance from rest. And we use the letter x to denote that, and x is measured in meters. When I've pulled it absolutely as far from equilibrium as I'm going to pull it, that displacement is now at its maximum, and our maximum displacement is called our amplitude. So we have a capital A for that, and that is also measured in meters. Now the period would be the time taken for one complete oscillation. So from one amplitude point all the way over to another and all the way back again. So this would be 1, 2, 3, 4 time periods, etc. That has the letter capital T, like you've seen before for time period in circular motion, and is measured in seconds. And the last one, frequency, is the number of complete oscillations per unit time, number of oscillations per second, and we have a little f, and we measure that in hertz, the unit of hertz being 1/seconds. We've got our pendulum again, currently at rest. If I displace it away from its equilibrium point to its maximum displacement, its amplitude, and I let it go, I can count the time periods when it returns to the place where it currently is now. So 1, 2, 3, 4, 5 time periods, and so on. If I try and make a graph of the motion of the pendulum, I can start off here. We'll call this positive because this would be increasing in the x direction, and negative over here, going more negative in the x direction. If I try and make a graph of this, if I start off at this point here at maximum positive displacement in x, start that there. The next convenient point that I can look at is 1/4 of the oscillation, when the bob will find itself back in the equilibrium position at 0. So I can put that, graph that something like there. After half an oscillation, it'll be over here somewhere, the same distance into the negative as this was into the positive, meaning that we get to the negative amplitude. That will be after half an oscillation, so I can put a mark there. After 3/4 of an oscillation, it'll be back at the equilibrium position, so I can put a mark about there, again on 0 displacement. And then after one full oscillation, it'll be back in the positive amplitude position. This has a really interesting shape, this graph, because if I was to draw like this, nice smooth path, you're all going to have seen this before. So that is a cosine graph. And that leads me to the next thing about oscillations, which brings us back to circular motion. So, if I plot the motion of this as its displacement along the x-axis, if I've got this little ball here and I plot it as displacement along the x-axis, I could start it at this position here, where the radius of this is length a, the amplitude, so that would be positive a, that would be negative a. The displacement in x here would be a cosine theta, where it's this angle there is theta. And I can look at that all the way around the circle. Now, we know that that is an angle of 0 degrees here. If we move into radians, 90 degrees when it hits the y-axis will be pi by 2. At 180 degrees, that would be an angle of pi radians. This one would be 3 pi by 2, 240 degrees. 270 degrees even. And this one would be 2 pi. So, if I bring my cosine graph back, I can mark these points on here and we can see that that is pi by 2, that would be 90 degrees, that will be pi, this will be 3 pi by 2, and this will be 2 pi. So you can see a link there between oscillatory motion and circular motion.